Have you ever wondered how massive companies keep track of literally millions of pieces of data without it all just turning into a complete tangled mess? Well, it all comes down to something called database design. Today, we're going to pull back the curtain on a really key concept that helps keep all that data clean, consistent, and reliable. So let's get into it.
All right, we're going to start our story where a lot of databases begin, with a simple table. Something that looks like it's getting the job done, but is actually hiding some pretty serious problems just beneath the surface.
And that's a real question you should ask yourself. Because without the right structure, the information that you count on can get inconsistent, unreliable, and, well, just flat out wrong.
Okay, just take a look at this table. It's tracking students, right? But notice how for every single student in the CSE branch, we're repeating the head of department's name, Mr. X, and his office number. Now, with just a few rows, this might not seem like a huge deal. But imagine this table with thousands or even millions of students. Yikes.
This kind of repetition actually has a name. It's called data redundancy. And it's not just wasteful. It's the root cause of what the pros call anomalies, or as I like to call them, data nightmares.
And these anomalies, they come in three particularly nasty flavors. First, you've got an insertion anomaly. This means you literally can't add a new department to your database until a student actually joins it. Kind of weird, right? Then there's the update anomaly. Say the HOD changes. Now you have to hunt down every single student record and change it. If you miss just one, your data is now inconsistent. And finally, the deletion anomaly. This one's scary. If the very last student from the MEC department drops out, all the info about that department, the HOD, the phone number, it just vanishes. Gone forever. Not good.
So, you're probably wondering, how in the world do we fix this mess? Well, the solution is an incredibly powerful process called normalization. Think of it as the deep cleaning that every good database needs.
A really great way to think about normalization is to just imagine you're tidying up a messy room. You're creating a specific place for everything. You have one drawer just for student info and another shelf just for department info. That way, there are no duplicates and everything is way easier to find and to manage.
So what are we actually doing when we normalize? Well, at its core, we're taking those big, clunky, redundant tables and strategically breaking them down. We're decomposing them into smaller, much more focused tables. And the goal is always the same: slash that repetition and make absolutely sure our data is trustworthy. Now, this whole cleanup process isn't just one big step. It's more like a ladder you climb, a series of stages called normal forms. Each new step applies even stricter rules to get your data more and more organized. It's kind of like leveling up in a game, where each level gets you closer to a perfectly structured database.
For a lot of databases, the big goal is to reach what's called the third normal form, or 3NF. It solves the vast majority of those nasty anomalies we talked about. So we're going to do a quick speed run through the first three forms to see how we get there.
All right, let's climb that ladder fast. First normal form, or 1NF, is super simple. Just make sure every little box in your table has only one piece of information. No lists allowed. Then, in second normal form, we make sure that all the data in a row is fully related to that row's main identifier, its primary key. And finally, third normal form cleans up those weird indirect relationships. For instance, the HOD's phone number has no business being in the student table. It belongs in a department table.
And once a database hits 3NF, it is in fantastic shape. Redundancy is way down, and those insertion, update, and deletion anomalies are pretty much a thing of the past. For most applications out there, 3NF is the gold standard. But what if it's still not quite enough?
And that, my friends, brings us to the main event, Boyce-Codd Normal Form, or BCNF for short. This is an even stricter, more advanced version of 3NF, and it's designed to hunt down and fix some really rare but tricky situations that 3NF can sometimes miss.
Okay, check out this table. Believe it or not, this is technically in third normal form. We've got students, the subjects they take, and the professor teaching that class. Now, a student can take multiple subjects, and a subject might be taught by a few different professors. But here's the hidden rule, the catch. In this system, each professor teaches only one subject. And that creates a subtle dependency that 3NF just doesn't catch. This is exactly where BCNF gets stricter. It introduces one simple but incredibly powerful rule. In database lingo, it says that every determinant must be a superkey. What does that even mean? It means if any column can be used to figure out another column's value, that first column has to be powerful enough to uniquely identify the entire row all by itself.
So here it is, the formal definition. For any relationship where X determines Y, X must be a superkey. Now let's apply that to our example. The professor column determines the subject, right? If you know the professor is P Java, you know the subject is Java. But professor is not a superkey. Knowing the professor is P Java doesn't tell you if it's student 101 or student 104. And that is the BCNF violation.
Let's just boil that all the way down. In plain English, it means this. If one piece of information can tell you what another piece of information is, then that first piece must be strong enough to act as a unique ID for the entire row. Period. No exceptions allowed.
So how do we fix it? We decompose. We break that one problematic table into two clean ones. Look here, we create one table that just links students to their professors using a professor ID. Then we make a second table that links each professor to the one subject they teach. Now the professor is the key of its own little table, the BCNF rule satisfied, and our data is squeaky clean.
So we did it. We've tidied our data up to this incredibly high standard. We've achieved perfect order. But as with so many things in the real world, this level of perfect organization comes with a trade-off.
You see, highly normalized data is fantastic for data integrity. When you need to update a piece of information, you only have to do it in exactly one place. But when you need to read information, you often have to stitch those small tables back together. This process is called joining, and it can slow things down. That's why sometimes, for pure speed, designers will intentionally denormalize data, accepting a little redundancy in exchange for faster results.
So let's just recap the journey here. We started with a complete data disaster, a table filled with those nasty anomalies. Then, we saw how normalization gave us a step-by-step process for cleaning it all up. And finally, BCNF came in with the strictest rules to give us the ultimate data integrity. It's all about one thing: eliminating redundancy to make sure our data is reliable.
And this leads us to our final big picture thought. Achieving perfect data integrity with a tool like BCNF is an amazing goal. But in a world that is obsessed with split-second performance, database designers constantly have to ask themselves, is this perfect structure actually worth the potential cost in speed? And that is the critical balancing act at the very heart of modern database design.